All right, so today's plan, pretty straightforward. Just finish up the section on decimal operations and work through 5-3 decimals and fractions. Um, just a short reminder, remember that the Examity practice exam is available. I know I've gotten a couple emails from folks with some questions about the Examity practice exam, so I wanted to just kind of discuss that really quickly here, just to kind of review the process. So when you log on to Blackboard, you'll see a site for Examity sign on. Click that link. That'll bring up a Blackboard page with a link to the Examity, third-party website. So you click that, you get over to the Examity website. You can create your profile and all that kind of stuff over there. And also on the Examity website, you can download the browser extension for Chrome. So I would recommend using Chrome. I think maybe some other browsers have the ability to kind of like run Chrome extensions, but that seems a, a little more technologically complex. So if you can use Chrome, that's probably the best option. And then when you download that browser extension, it'll pop up in kind of the top right-hand kind of corner of your browser. When you start an exam, you'll be able to click that, and there will be a little button that comes up that says like insert password. So when you do all of the Examity stuff, you kind of get your session started, get the screen share started, all of that. When all the Examity stuff is set up, then what you do is go to a different tab, jump over to WebAssign, log in with your standard username and password on WebAssign. When you get into the system, if you click on the Examity practice exam, it will ask for a password. Note that the password that it's asking for is not like, it's not your password for Blackboard. It's not your password for logging into WebAssign. It's a password that's specific to that exam. And Examity's browser extension, that insert password little button, I think it's like a yellow button. It has like a key kind of symbol on it. It says something like insert password or enter password. If you click on the password field so that it's like ready to type in WebAssign, and then you click on that browser extension, insert password button, it should pop the password right over there for you. Um, if it doesn't, let me know, send me a screenshot or something, tell me what you tried and what's not working, or if there's an error, if it comes up with an error or something like that. But it should pop that password in there for you, and you should see like those bunch of dots whenever you type in a password, and it kind of hides the characters. Then you should be able to just hit submit password or whatever on WebAssign and get into the test. So I just wanted to kind of go through that process one time, explain it kind of more clearly at the beginning of a lecture, and you can come back to this if you have any, if you want to hear that again. I think we did talk about it a little bit kind of like after class, maybe last time or something, but I don't know if everybody was here for that. So just to run through it one more time. And like I said, I really wish I could do a recording of me doing it, but the way that our Blackboard works, it doesn't actually let me do that. I might actually try to work with another faculty member and see if like I can get them to like add me to a dummy class of theirs or something, and like so I could be like a student in their class. I don't know, so I might try to do something like that. Um, tech is great when it works well, but okay, somebody asked me to say the password one more time for the practice exam. I think if you're asking me to tell you the password, you missed what I said. Um, so I don't want to run through the whole thing again, but Examity will enter the password for you. And if you didn't kind of catch that procedure, when I post the recording, you can come back and kind of, go back through what I said, but the Examity browser extension will enter the password for you. So you'll never actually see the password. Examity enters the password into WebAssign for you. But it's not one of your passwords. It's not like your WebAssign password or your Blackboard password. You should never even see the password. You shouldn't have to type anything in. Okay. Okay. Yeah. All right. So moving on to decimals. So 5.2 and 5.3. So one thing, just to kind of recap what we talked about last time, just a reminder that fundamentally decimals are kind of this similar idea, similar uh, underlying idea to fractions. They're very similar in nature, that they represent parts of a whole. So we can think of decimals along with, say, their fraction equivalents. As we kind of lose powers of 10 from the natural numbers, we can think of that as like losing powers of 10 from the numerator in a fraction. And if we continue dropping powers of 10 from our natural numbers, once we get down to 1, we start moving that 1 from, the hundreds place to the tens place to the ones place. Well, we move it over one more to the other side of the decimal point, to the tenths place, or again to the hundredths place, and so on. Or in fraction form, we begin adding zeros to the denominator of the fraction. And this is our place, our place names kind of lined up in a more pictographic format. Okay, so sorry. So we talked last time about adding and subtracting decimals. And the really nice thing about adding and subtracting decimals was it really worked very similarly to adding and subtracting whole numbers. We just basically had to align the decimal points and then bring that down in the answer. Now, multiplying decimals works a little bit differently. It's pretty similar to the procedure for multiplying whole numbers, but the what to do with the decimal point is a little bit more complicated. So if we look at our strategy for multiplying decimals, first we determine the sign of the product, same as before. If we had, 8 times -3, we have a positive times a negative, the answer is going to be negative. We write the numbers in vertical format, lining up the numbers on the right. Now, note here, we just line up the numbers starting on the right. We don't stick any extra zeros on, we don't line up the decimal points. So we line up the numbers on the right. Not the decimal points. So this is maybe an unfortunate thing about operations on decimals is, and when we look at each operation works quite similarly to the, say, similar operation on whole numbers, but there's a little nuance that's different, and the little nuance that's different is different between the different operations, right? Add or subtract, we line the decimal points up, and we add in zeros as buffers if we need them. But here, when we're multiplying decimals, we just kind of push everything over to the right. We don't care if the place values line up vertically with one another quite, just right. Then we multiply the numbers as if they were whole numbers, basically just ignoring the decimal points for the time being. And here is where we handle the decimal point. We've placed the decimal point that the number of decimal places in our final product, in our final answer, is the sum of the number of decimal places in the factors. And then we write the product with the appropriate sign. So let's start with a pretty simple one, say like 0.6 times 0.7. And let's actually multiply this using both fractions and decimal multiplication. So let's start by reimagining 0.6 and 0.7 as fractions, doing fraction multiplication, seeing what answer we get. 0.6 is 6/10, or that is 6/10. And 0.7 is 7/10, that is 7/10. Well, this is 6 times 7 over 10 times 10, or 42 over 100, 42 hundredths. But wait, 42 hundredths is 0.42. So I see really what I did is I've kind of accounted for the decimal in the 0.6 with this tenths here. I accounted for the decimal in the 0.7 with this tenths here. These two tens came together to make a 1/100th, and that gave me 2 decimal places in my answer. one of them coming from here, one of them coming from there, or one of them coming from this first tenths, one of them coming from this second tenths. So with fractions, it's a little more clear why we say the number of decimal places in the product is the sum of the number in the factors, is because we have one decimal place being kind of encapsulated in that tenths associated with the 6, and one more being encapsulated in that tenths associated with the 7, and 1 plus 1 gives me 2 decimal places that's in relation to that hundredths from the 10 times 10 in the denominator. Okay, so let's directly use our decimal multiplication now. So 0.6 times 0.7. My decimals happen to line up vertically here, but that's not a requirement. We just push everything to the right-hand side. And then to do 7 times 6 is 42. This is a simple problem, so that's all that I have to do. And then I count my decimal places. 1 decimal place in the 0.6, 1 decimal place in the 0.7. So I should have 2 decimal places in my answer. 1, 2. 0.42 as my answer. Okay, let's move on to one that's a bit more challenging. So here I want to do 0.81 times 0.3. And remember, we just line everything up as far to the right as we can. Basically, we're doing like 81 times 3, right? We're basically thinking of this as like 81 one hundredths. Got an extra 0 in there. And 3 tenths. So we're really just kind of multiplying the numerators, 81 and 3. Being able to go back and forth with these decimals and fractions, thinking of it one way when it's convenient or the other way when it's more convenient, is super helpful. Now I basically just ignore the decimal points for the time being. I do 3 times 1 is 3, 3 times 8 is 24, and that's all that I have. Then I need to figure out where to place the decimal. The 81 has 2 decimal places. 0.3 has 1 decimal place. My answer should have 3 decimal places. 1, 2, 3. 0.243. What would this look like if I instead had 0.81 times 0.03? So an extra 0 in between the decimal point and the 3, or this is multiplied by 3 hundredths instead of 3 tenths. All that kind of really does is turns this 10 into a 100, adds another decimal place. Three times 1 is 3, 3 times 8 is 24. Just like before, we have 2 decimal places in the 0.81, but now we have 2 decimal places in the 0.03. We ought to have a total of 4 decimal places in our answer. I start here, 243, move my decimal point 1, 2, 3. I need to go another one. So I just put a little buffer 0. 243 is the same as 0 thousands and 2 hundreds and 4 tens and 3 ones, etc. So that gives me another place to move. So this is what it means where it says, if needed, use zeros as placeholders. 243 only has 3 digits, but I need to move 4 places. So I'll make 243 instead of 243. I'll make it 0243. And I can move over to the left those 4 places. Okay, what about this product? 0.04, sorry, negative 0.04 times 36.89. So I know my answer is going to be negative because I have a negative times a positive. And then I'll just take 36.89. I'll put that on top because that has more numbers to it. And 0.04 on the bottom, and I'll multiply these. Again, in this case, my decimal points happen to line up, but that doesn't matter. I just push everything to the right. 4 times 9 is 36. Write the 6, carry the 3. 4 times 8 is 32, plus 3 is 35. Write the 5, carry the 3. 6 fours are 24, plus 3 is 27. Write the 7, carry the 2. 4 threes are 12, plus 2 is 14. So multiplying these two numbers together, multiplying them as if they are 3,689 times 4, this gives me 14,756 if those were whole numbers. I can ask myself, is that reasonable? Right, 3,600 times 4, somewhere in the ballpark of 15,000. That seems pretty reasonable. 3,500 times 2 would be 7,000. Times 2 again would be like 14,000. So seems about right. Now I have to fix my decimal places. So I have 2 places here, 2 there. I need to have 4 in my answer. 1, 2, 3, 4. So my answer is going to be like 1.4756. And I know it should be negative, so I make it negative. So there's a lot of individual little pieces to remember, right? I need to do my multiplication. I need to fix the decimal point, put it in the right place. I need to potentially fix the sign. Is it supposed to be negative? I need to remember these little pieces, but each piece I think is pretty straightforward. Each piece is really just closely related to things that we've discussed before, either with fractions or whole numbers, but we just need to keep straight what the pieces are, don't forget any of them, and do them in the right order. What about we multiply by powers of 10, like 10 or 100 or 1,000? Well, if I have 9.248 times 10, well, I see that I just end up with 0 times a bunch of stuff is 0. 1 times these things are, or is just that thing, right? I have 3 decimal places here. I need 3 decimal places here. 92.480, or I'll just knock off that last 0. We don't need that. Effectively, this just moved the decimal point 1 place to the right. When I'm multiplying by a power of 10, like 10 or 100 or 1,000, the 1 that multiplies through doesn't change any of the numbers. The numbers just copy down. The only thing that we do is we end up kind of sticking an extra 0 or maybe a couple zeros off here to the right before we start counting the decimal places. This isn't a whole number. It has no decimal places. So we count over the same number of decimal places, but we have an extra 0 or a couple of zeros put in there as a buffer that effectively just moves our decimal points location. If I have the same thing multiplied by 100, I would just have had an extra 0 here. That would mean 1, 2, 3 places would put the decimal point 1 further to the right. Or in other words, multiplying by 100 just moves this decimal point 2 places to the right. 924.8. Or multiplying by 1,000, 1,000 has 3 powers of 10, 3 extra zeros that would get put onto the end of that answer before we move the decimal point. So 1, 2, three places to the right, 9,248. Kind of an interesting little side note is, so if we were writing a number that's in thousands with a decimal point, we might write something like 10,324.75. In some parts of the world, I think, places that are kind of related to the UK or Britain or colonies, um, they might write this as like 10.324 comma 75. They seem to do like their commas and their dots kind of the opposite of the way we do it. Um, so if you're ever, looking on the internet, there are some really good math channels that come out of the UK, like Numberphile or oh, what's his name? Stand Up Maths with his last name's Parker. I can't remember his first name now, but so there are some good math channels from the UK, and sometimes you'll see them writing decimals, and even to me, even though I know how it works, it always looks strange to me. So, um, you know, we're using comma as the separator between the groupings for whole numbers and decimal point as the separation between the whole numbers and the parts. But, the world is becoming much smaller than it used to be. So if you're perusing YouTube or, online resources or anything like that, you might see a slightly different usage of dots and commas to mean slightly different things. So um, there's not really like, I know it seems kind of strange, but there's not really an authority like a dictionary or like a Webster's dictionary for math that says like this symbol means this thing everywhere. So it's kind of a little, it's a very interesting linguistic thing that like somehow like across, at least across all of the US or for most things across the whole world, aside from minor, uh, interesting points like this, um, we all kind of like seemingly speak roughly the same mathematical language, um, even though there's no authority saying you must do it this way. We kind of have all more or less agreed to kind of speak the same language in the same way, just somehow like implicitly. Um, but then the downside is when there's not such an authority, like sometimes you have different subfields that use similar notation to mean very different things or different notation for the same thing. And so even within math, particularly the more advanced math, the more stuff you're trying to do, there's only so many symbols on the keyboard that are easy to type or easy to write or easy to recognize. So, um, sometimes we have more ideas than we have symbols, and then things get a little bit complicated. One example is like this thing. Well, this is a little more advanced than where we're at now, but you might have seen in the past that something like parentheses 3 comma 4 end parentheses could mean an ordered pair on a graph, or it could mean an interval on the real line, and it's ambiguous unless you have context, unless what the problem is asking for. But so a little bit of an aside on notation um, and kind of the linguistics of mathematics. As another short aside, one of the things that drives me bonkers is these problems where they do like, I don't know, like 12, you know, I don't, how would they write it? Like 12 over like 6, I don't know, 3 plus 9 or something like that. I don't know. And they try to like, they say, what does this mean? And everybody, of course, is arguing because half of the people want to do like 6 times 3 plus 9 and 12 divided by that. And half the people want to do like 12 divided by 6 and then multiply that by 3 plus 9. And my usual argument is, well, why would you intentionally write a mathematical sentence, which is kind of what this is, or a phrase, that is ambiguous, right? Right. Like, uh, I don't know, it would be really silly for an English professor to say, what does this phrase mean, or to say like, what does the word cleave mean? and then like mark you wrong if you guess the wrong, the wrong meaning or something. It'd be more reasonable to say what does the word cleave mean in the sentence? The axe cleaved the login two, or the two were cleaved together in marriage or something like that. You cleave together, or they just cleaved in marriage. I don't know. I'd have to think about that. But the point is, like, when we're using math, I mean, we're using it within a context, right? I mean, maybe not here. We're kind of practicing some things, but when we're actually using it, we're using it within some context. Even if it's a very abstract context, it's still within a context. And what does this string of symbols mean? Well, that's a logistic, or that's a linguistic question. And if half of people say that it means this, and half of people say that it means that, then maybe the person posing the question should have made the context more clear. So anyway, so sorry, that's a little bit of just um, details on the notation and linguistics of mathematics. But you will see occasionally some different syntax, some different uses of symbols, particularly because, our large world has gotten a lot smaller with the internet. So you can interact with folks from different backgrounds, from different education systems, from different perspectives. So just be aware of that if you're looking at resources online. Okay. Any questions on multiplying decimals? Multiplying by powers of 10 is super easy. Multiplying decimals by decimals, we pretty much just treat it like multiplying whole number by whole number. We correct the decimal places at the end, adding 0 buffers if needed, and correcting our sign if needed. Okay, let's look at dividing decimals. And maybe before we do that, let's take a look at just essentially how multiplication relates to division. Remember, if we have A times B equals C, well, that would mean that C divided by B equals A, or that would mean that C divided by A equals B. So we usually think of division as kind of being related to a more understandable, maybe, multiplication problem. So let's take each of these multiplication problems and rewrite them as two different associated division problems. 3 times 5 equals 15. I could write that as 3 equals 15 divided by 5, or as 5 equals 15 divided by 3. And I think we would agree that 15 divided by 5 does equal 3, and the 15 divided by 3 does equal 5. What about decimals? Well, this same idea applies to decimals as well. A, B, and C could be whole numbers. They could be decimals. 0.3 equals 1.5 divided by 5. So if I take 1.5 and I divide it in 5 parts, I get 0.3. Sometimes it's helpful to think of decimals in terms of currency. If I have $1.50, $1.5, and I want to split that evenly between, say 5 kids for Christmas, they're probably not going to be very thrilled with not getting very much money for Christmas. But if I have $1.50, I want to split that between 5 kids, they can each get 30 cents, $0.3. Or I can say that 5 equals 1.5 divided by 0.3. In other words, how many times would I have to accumulate $0.3 to make $1.50? I would have to get $0.3 5 times in order to make $1.50. So when I have a decimal divided by a decimal, I can say, like, how many times would I have to accumulate the divisor to make the dividend? In this case, that would be 5. I have to collect 30 cents from 5 people to make $1.50. Or I could look at this, 0.3 times 0.5 equals 0.15. 0.3 equals 0.15 divided by 0.5. Or 0.5 equals 0.15 divided by 0.3. So if I ever am looking at a decimal division problem and I'm getting confused, I can kind of reimagine it in terms of an associative multiplication problem and say, okay, what's really being asked for here? Okay. So this is kind of saying, how many times would I have to collect 50 cents in order to earn 15 cents? Or maybe you could say something like, if I work 1 hour, I earn 50 cents. If I only need to earn 15 cents, how many hours do I have to work? Only 0.3 hours. Hopefully you're not making that wage now, maybe back in, 1920 or something like that. That was the wage, maybe. Or a similar question over here. If somebody in 1920 was paid 30 cents an hour, but they only needed to make 15 cents, how many hours do they need to work? A half an hour, 0.5 hours. Okay, so what do we do? What's our procedure for dividing a decimal by a whole number? We're going to start with this scenario, decimal divided by whole number, before we go to decimal divided by decimal. Okay, so the first step that we do is we write the problem out as a long division. And again, we just basically do our long division as usual. We just make sure that we're extra careful with placing the place values in the answer above the associated place value in the question. And then we place our decimal point where it needs to be. So let's actually do one of these. Maybe we'll pick this one to do. Say, come off to the side here. What is 1.5 divided by 5? That's it, divided by 1.5 divided by 5. And I say, does 5 go into 1? No, it doesn't. 5 goes into 1, say 0 times. Does 5 go into 15? Yes, it does. It goes in 3 times. I bring my decimal point up. I was careful to align my places when I'm asking, does 5 go into 1? 0 times 5 goes into 15 3 times. 3 times 5 is 15. Or I could say 0.3 times 5 if I wanted, but the 15 minus 15 gives me 0. 0 remainder, nothing else to bring down. So my answer, 0.3, as we'd expect from over here. So what about 0.27 divided by 3? Maybe I'll write my decimal point a little bigger. I tend to write my decimal points kind of small, but I'll try to write them a little bigger so you can see them a little better on the screen. 3 goes into 0, 0 times. I run into my decimal point. Let me bring that up. 3 goes into 2, 0 times as well. 3 goes into 27, 9 times. 9 times 3 is 27. I have 0 remainder, nothing else to bring down. My answer is 0.09. If I wanted to, I could check this. My claim is that 0.27 divided by 3 equals 0.09. I can ask, is it true that 0.27 equals 3 times 0.09? Well, let's check. 0.09 times 3. 9 times 3 is 27. I have 2 decimal places, 0 decimal places. I should have 2 in the answer. 1, 2, 0.27. That does look good. So I can also check my answer with the associated multiplication problem. And that does seem to check out here. So I'm pretty confident in this answer of 0.09. What about 4.75 divided by 25? Does 25 go into 4? No, it doesn't. Or we could say it goes in 0 times. Does 25 go into 47? I've run into my decimal point. Let me just bring that up. Yes, it does. It goes in 1 time. 1 times 25 is 25. 47 minus 25 is 22. And I bring down my 5. Does 25 go into 225? Yes, it does, a bunch of times. 25 times 10 would give me 250. 25 times 4 is 100, so 25 times 8 would give me 200. So I think this is going to be 25 times 9. 9 times 25 is indeed 225, giving me a remainder of 0. So this quotient is 0.19, or 19 hundredths. What about something like this? 12.04, or 12 and 4 hundredths, divided by 43. So does 43 go into 1? No, it doesn't. Or you could say it goes in 0 times. Does 43 go into 12? It goes in 0 times. I've run into my decimal point. Let me just bring that up. I'm being a little more pedantic here about checking every single digit so that I keep track of what place I'm at. Does 43 go into 120? Yes, it does. It almost goes in 3 times. 40 times 3 would be 120, but 43 times 3 is 129. It's a little too much. It's going to go in twice. 2 times 43 is 86. And 120 minus 86, well, 86 plus 4 gives me 90. Plus 30 gives me 120, so I think that's going to be 34. And fingers crossed that this all works out okay. Let's see. So 344 now, we need to bring down the 4. Does 43 go into 344? Well, yeah, it does. So we're looking for 344. 43 times 10 is 430. So that's a good bit too high. 43 times 5, what would that be? 15, 21, 215. So we need more than that. Let's try 43 times 7. 7 threes are 21. 7 fours are 28. Plus 2 is 30. And let me adjust my spacing here a little bit. Four and 3 times 7 makes 301. And I can see that 43 times 8, I need to add another 43 onto 301. That's 344. So it was a decent bit of work to find this, but we did find that 43 goes into 344 exactly 8 times. And 8 times 43, 344, remainder 0. Nothing else to bring down. So we see our answer is 0.28. So dividing a decimal by a whole number, not too bad, right? It's pretty much just a whole number long division problem. We just have to be a little more careful about keeping all of our place values lined up properly so that when we bring this decimal point up, it comes up in the correct place. So we just need to be a little more orderly about keeping our columns kind of oriented nicely. And then our decimal point just kind of comes up and plugs itself into the answer basically. Okay, so what do I do then if I have two decimal numbers? Well, the nice thing is it's going to be pretty similar to dividing a decimal number by a whole number because we're going to manipulate our fraction. This is really kind of a fraction with a decimal in the numerator and a decimal in the denominator. We're going to manipulate it into an equivalent fraction that has a whole number in the denominator. Right, and 0.8 divided by 0.4 is basically just the fraction 0.8 over 0.4. If I want to construct an equivalent fraction, but whose denominator is a whole number, well, I have 0.4, not a whole number in the denominator. I want to multiply by some power of 10, by a 10 or 100 or 1,000 to turn this 0.4 into a whole number. I see that I need to move the decimal point one place to the right in order to give me just a 4, just a whole number. To move one place to the right, I need 1 power of 10 or just 10. But remember, I can't just stick the 10 in the bottom. To make an equivalent fraction, I need to multiply top and bottom by the same thing. The top needs to be multiplied by 10 as well. 0.4 times 10 is 4. And then 0.8 times 10 is 8. And here, actually, nicely enough, getting rid of the decimal on the bottom also got rid of the decimal on the top. That was a pretty nice occurrence. That doesn't happen all the time, or even maybe most of the time. But here that happened, and 8 over 4, we see is clearly just 2. 0.8 divided by 0.4 is just 2. So what is my strategy here? While I reimagine this division of two decimals as a fraction with a decimal in the numerator, decimal in the denominator, I multiply my denominator by a power of 10 to get rid of the decimal, to move that decimal point all the way to the right. Multiply the numerator by the same power of 10 to make an equivalent fraction. And then I can either just simplify the fraction, maybe I can get away with that. Or maybe I want to go back into, if I'm left with, say, a decimal in the numerator, I'll go back into the division sign notation, perform my long division as I did previously with a decimal divided by a whole number. Okay, let's look at this next problem. 1.25 divided by negative 0.5. So again, we have the division of two decimals. We also have a negative here. So we'll just remember that, well, if I have a quotient where one of my two factors is negative, my answer has got to be negative. So I'm going to divide these as though they were positive numbers, and then I will fix the sign. I'll make the answer negative at the end. So if I'm interested in 1.25 divided by 0.5, again, this is a quotient of two decimals. I have a decimal in my divisor. So what am I going to do? I need to move this decimal point 1 to the right and the bottom. Okay. Get that parentheses away from the 1. There we go. This means I want to multiply the bottom by some number that moves the decimal point 1 to the right. Well, that would be the number 10. Multiplying by 1 power of 10 moves the decimal point 1 place to the right. To make an equivalent fraction, I had better also multiply the numerator by that same number. Right? This feels very similar to what we did when we were adding or subtracting fractions with unlike denominators. We wanted an equivalent fraction that satisfied a certain property, maybe that it had a common denominator, or here we want it to satisfy the property that the new denominator is a whole number. So we make our equivalent fraction the same way. We multiply top and bottom by the same thing. Here we multiply by 10. My numerator, the decimal point moves 1 to the right. That's the contribution from the 10 up top. 12.5 over my denominator over 5. And here, this isn't a simple fraction to simplify, like I kind of got lucky up at this first one. So what do I need to do now? Well, now I just convert back. 12.5 divided by 5. I don't want to forget that I have a negative that I need. But I do 12.5 divided by 5. Now we're back in our previous strategy where we just have division by a whole number. We do our long division. 5 goes into 1 0 times. 5 goes into 12 twice. 2 times 5 is 10. 12 minus 10 is 2. My decimal point comes up. My 5 comes down. 5 goes into 25 5 times. 5 times 5 is 25. 0 remainder. Nothing else to bring down. Our answer is 2.5, but with a negative sign. So our answer is negative 2.5. So again, lots of individual moving pieces, maybe 4 or 5 different steps that we had to do here, but I think each one was pretty straightforward. So if we, do a handful of these problems, the strategy becomes more clear the more of them we do. We get more used to doing them, and they become a little easier over time. Okay, what about a problem like this? 6.5 divided by 3.25. So again, I see I have decimal over decimal. Now, when you get a little more savvy at this, if you get more used to dealing with this, you can just move the decimal point up here, and you see that if I have the dividend over the divisor, if I move the decimal point 1 to the right in one of them, I've got to move it 1 to the right in the other one, or move to the left in one, got to move it to the left in the other one. So you can skip some of this converting to a fraction and converting back later on, but I want to show really where all of this is coming from, based on kind of first principles. So again, I want to convert this to an equivalent fraction where my denominator is a whole number. I need to move my decimal point in the denominator 2 places to the right to make a whole number. So I need to multiply by 2 powers of 10, or that is 100, shifting 2 place values. To make an equivalent fraction, the numerator also needs to multiply by 100. And the denominator, 3.25 times 100 becomes 325. In the numerator, 6.5 times 100. Remember, 6.5 is the same as 6.50. I can put a buffer 0 in there so that I have 2 places to move to the right. So I need 650 divided by 325. And I might realize, oh, wait, 325 times 2 is exactly 650. So in this case, we ended up with a fraction that was easy to simplify. Any questions so far? Okay, let's take a look at 5 divided by 0.04. Here we have a whole number divided by a decimal. So when we set up here dividing, decimal numbers, really what we're interested in is dividing by decimal numbers. So if anytime we're dividing by a decimal number, we're going to use this strategy, right? It's really a question of what is the divisor, what is being divided by. If it's a whole number, we use this strategy. We use our just straightforward long division, don't have to adjust any decimal places. If we're dividing by a decimal, we need to adjust the decimal places first and then proceed with our long division. So since we're dividing by a decimal, again, we kind of reframe it as a fraction. We need to move 2 decimal places to the right in our denominator. I'll leave myself a little extra room next to this 5 in its parentheses. To move 2 places to the right in my denominator, I need to multiply by 2 powers of 10, or that is 100. And to keep this as an equivalent fraction, I need to multiply the numerator by the same thing that I'm multiplying the denominator by. Now I know that I want to move 2 places to the right in the denominator. I see 2 places there. I also want to move 2 places to the right in the numerator, but I just have a 5 there. I could either think of doing like 5.00 times 100, or just 5 times 100 is just 500. Whichever way you like to think about it. If you want to put in the decimal point and the buffer zeros and then move the point, or if you just want to think of integer multiplication, 5 times 100 is just 500. And then 0.04 times 100, we move the decimal point 2 places to the right. That gives me a 4 in the denominator. What is 500 divided by 4? Maybe you can kind of figure this out, or maybe we can divide out some factors. But if we wanted to, we can go over to long division. This is probably not the most efficient way here. Probably dividing out a couple of factors in our fraction would be the better way to go, but just showing that we could do this if we wanted to. Keep in mind the decimal point is like there, right? 500 is a whole number. Its decimal point, we don't usually explicitly write it, but it's after that ones place. 4 goes into 5 how many times? Once. 1 times 4 is 4. 5 minus 4 is 1. Bring down to 0. 4 goes into 10 how many times? Twice. 2 times 4 is 8. Bring down to 0. 4 goes into 20 how many times? 5. 5 times 4 is 20. 0 remainder, nothing else to bring down. And we see, we could bring our decimal point up, but really we don't have anything after that decimal point. This is just the number 125. So if we were, in some strange country that had currency that came in values of 4-cent pieces, like instead of a nickel or a penny, if they had 4-cent pieces, how many of those 4-cent pieces would be needed to make 5 of that country's dollars? We'd need 125 of them. Okay, so then what about 14 divided by 0.35? Pretty similar idea. I know I want to move the decimal place 2 to the right, or decimal point 2 places to the right in the denominator. I want to multiply by 2 factors of 10, or that's 100. Do the same thing in the numerator. In the numerator, I have 1,400. And in the denominator, I have just 35. The other way that I could think about this is I could think about it as just a fraction now with whole numbers in the numerator and denominator. I see the 35 as, say, 7 times 5, and I could think, well, 1400, that's kind of like 200 times 7, right? That's like 2 times 7 times 100. So my 7's divide out. But I now have 200 divided by 5. Well, 200, that's like 2 times 100. But 100 I know is 20 times 5. I can divide out the 5s as well and get 2 times 20 or 40. I could have just as well, I could have done this one up here this way, divided out a factor of 2, divided out another factor of 2 and got my answer. I could have done my 14 divided by 0.35, this 1400 over 35 is a long division. I could really do it either way because I had a situation where I ended up with integer over integer, and then it's kind of my choice how I would like to proceed from there. So I can simplify the fraction, I can do long division. I could even, I suppose, if I wanted to, do a combination of the two. I could maybe realize that a factor of 7 can come out of both of these, but then I say, wait, what's 200 over 5? I could do 200 over 5, and maybe that's a more manageable long division. Right? I could kind of use any combination that fits the problem. Okay, and what about a problem like 0.6 over 0.2? Again, when we get used to it, we can just realize that we can shift the decimal point a certain number of places to the right or left in the dividend as long as we also do it in the divisor and vice versa. I want this 0.2 to be a whole number. I just shift the decimal point 1 to the right to make that a 2. I better also do that in the dividend in the 0.6. So I have 6 divided by 2 equals 3. So this can be a pretty quick process. We don't have to write out all of this detail all the time. When we get used to it, we can just use this kind of shifting decimal points. As long as we shift the decimal point after the division sign the same number of places in the same direction as we shift the one before the division sign. Any questions on any of this? Okay, a couple of application problems. So let's suppose that Peter earns $8.75 per hour. Last week he worked 19 hours. How much money did he earn? Well, he would have earned in dollars 8.75 times 19. How do I multiply these? Well, I do my multiplication algorithm. 8.75 times 19. I multiply these as though they were just 875 and 19 multiplied together. So let's do that. 9 times 5 is 45. 9 times 7 is 63. Plus 4 is 67. Oh, 67. 9/8 are 72. Plus 6 is 78. Then I move over to my 1. I put a buffer 0 there just as a placeholder. 1 times 5 is 5. 1 times 7 is 7. 1 times 8 is 8. And I add straight down. 5 plus 0 is 5. 7 and 5 is 12. Carry the 1. 7 and 8 is 15. Plus 1 is 16. Carry the 1. And 8 plus 7 is 15. Plus 1 is 16. Little deja vu there, but that's how it turned out. So I get 16625, or in other words, 875 times 19 is about, or is 16,625. That does kind of make sense, right? So if I had, say, 900 times 20, that would be like, say, roughly 18,000. That's kind of in the same ballpark. Now I note that 8.75 has two decimal places. The number 19, the decimal point is kind of just like not written there. It's implicitly right there after the 9. It has 0 decimal places. 0 numbers that I see explicitly to the right of that decimal point that I used in the multiplication. My answer should have 2 decimal places. So 1, 2, starting at the end, we move 2 decimal places to the left. This should be 166.25. And I want to answer in dollars. So for this, say, half week or so of work, 19 hours, let's say part-time job, Peter earned 166.25 that week. Any questions on that one? Okay, so let's look at another payroll example. Maria got her first paycheck from her new job. She worked 25 hours and she earned $362.50. How much does she earn per hour? What was her hourly wage over this time period? Maybe she doesn't know this. Maybe it's a job that kind of has some commission, something like that. Um, so it's not just a strict hourly wage. You want to figure out, okay, I put in this amount of time, I earned this much from my commissions on my sales and all of everything combined, or tips or whatever it may be. So what was my hourly wage, right? Especially if Maria was like, say, a server in a restaurant and was looking at maybe switching to a different job where she would just get paid just hourly, how would that come out? Should she switch to a different job or not? Um, so that might be the context for something like this. Okay, so her hourly wage is dollars per hour. Our units kind of help us here because we know that how much does she earn per hour? This should be in dollars per hour. So I should have dollars on the numerator or in the numerator and hours in the denominator. Or 362.5 divided by 25. Here I have a decimal divided by a whole number. I don't have to fix any decimal places. I can just jump right into my long division. 362.5 divided by 25. Does 25 go into 3? No, or it goes in 0 times. Does 25 go into 36? Yes, it goes in 1 time. 1 times 25 is 25. Subtract that off and I get 36 minus 25 is 11. Bring down the 2. Does 25 go into 112? Yes, it does. 25 times 4 is 100. 25 times 5 is 125. That's too much. It just goes in 4 times. 4 times 25, 100. 112 minus 100 is 12. I'll bring down my 5. I see I've run into my decimal point. Let me bring that up. Does 25 go into 125? Yes, it does. 5 times. 5 times 25 is 125. Subtract, I get 0. Nothing else to bring down. 0 remainder. I'm done with my long division now. So my answer is 14.5. But really, I would phrase this as something like $14.50 per hour. So that was her kind of average hourly wage over this, first, say, week or so that she got the paycheck from. Any questions on multiplying or dividing decimals, or really anything so far about decimals? Okay. So let's move on to our next section. And here we're looking at the interplay between decimals and fractions. So we've already talked a good bit about kind of converting decimal whoops, I wrote this the wrong way. Convert fractions to decimals. We've already talked a good bit about converting decimals to fractions. So all the way back at the beginning here, really far back here, we talked about that our decimals are really just kind of, you know, that they have fraction equivalence. We use the idea of converting decimals to fractions when we were talking about, I scrolled a little too far. There we go. We were talking about introducing multiplication. And also when we were dividing by a decimal. What about going the other way? What if I'm given a fraction and I want to find the decimal equivalent? What if I want to say write 1/4 as a decimal? We might be able to kind of figure this out based on context. Maybe we say, okay, a quarter of a dollar is like 25 cents. I think it's going to be like 0.25. But let's go through systematically. It's always good to start with an easier problem going through systematically so that we kind of get our feet under us. What would I really like to do here with 1/4? I'd really like it if this 1/4 was, if I had something like 100 divided by 4, I know how to do that, right? I know that that's going to be 25. So I'd really like this numerator to have more numbers in it so that I could, I guess I wouldn't be really dividing out like I am over there. I wouldn't be dividing out factors, but maybe I could do long division. So I would like this numerator to have more numbers in it. I can do that by just putting in like, 0.0 or 0.00, something like that, divided by 4. Well, now it seems kind of artificial. It seems kind of silly, but I've manufactured a problem where I now have a decimal number divided by a whole number. I have a decimal over a whole number. But I know how to simplify these. I do long division, right? Now, again, this might all seem pretty silly. You say, where are we going with this? Well, I think we'll see here in a second. If I do 1 divided by 4, I kind of just don't have anything to work with. But if I do 1.00 divided by 4, remember, when I'm in my long division step, I kind of just treat this like it was 100 divided by 4 and, just kind of keep track of my decimal point. 4 goes into 1 0 times. I ran into my decimal. Let me write that up here. 4 goes into 10 twice. I wrote my zeros a little too close together. And rewrite those. 2 times 4 is 8. Make sure to write that under the correct place. 2 times 4 is 8. 10 minus 8 is 2. Bring down the 0. 4 goes into 20 5 times. 5 times 4 is 20. I have nothing left to bring down. I have a 0 remainder. My long division is done. So 1.00 divided by 4 is 0.25. But that's just the same thing as 1/4, right? 1/4 is just 0.25. So if I want to take a fraction that's a ratio of whole numbers, and I want to write it as a decimal, typically what I'll do is I'll just write that numerator as whole number dot and some zeros. And if I need to, I'll just keep sticking zeros at the end. Ideally until I end up with a remainder of 0, or maybe we'll see some cases where that doesn't work out so nicely. But I can rewrite 1, for instance, in my numerator as 1.0 or 1.00 or 1.000. I can just keep tacking on zeros after the decimal point, allowing me to go one step further on this long division cascade, hopefully eventually making my way down to a zero remainder and getting my answer. So what about -9/8? If I want to write this as a decimal, it's going to be a negative answer. So I want to make sure I remember that. And then I'll have 9 divided by 8. 8 goes into 9 one time. 1 times 8 is 8. And I have one remainder. One left over as a remainder. So I could write 9/8 as 1 with a remainder of 1. Or and this is like, that looks like absolute value of R. Let me write my ones a little better. 1 with a remainder of 1. Or I suppose I could write it as like 1 and 1/8 or something like that. But if I want it as a decimal, switch colors here. I'm going to write my 9 as 9.0. This gives me something to bring down. I see that 8 goes into 10 one time. I ran into my decimal point. I'll bring that up. 1 times 8 is 8. I still don't have a zero remainder. I can tack on another 0 after the decimal point. 9 is the same as 9.0 or 9.00. 8 goes into 20 twice. 2 times 8 is 16. 20 minus 16 is 4. I still don't have a zero remainder. I can tack on another 0 and bring it down. 8 goes into 40 5 times. 5 times 8 is 40, and there we go. I now have a zero remainder, nothing left to bring down. So 9/8 is 1.125, and I want my answer to be negative. So I kind of manufacture this long division problem with this decimal that's like 9.00, as many zeros as I need, until I make my way down to a zero remainder, or maybe in some other cases until I see that that's not going to happen. Okay, let's look at this one, right? 1/3 is a decimal. So again, I have 1 divided by 3. 3 goes into 1 0 times. So I write 1 as 1.0. 3 goes into 10. Well, it goes in 3 times. I've run into my decimal point, so let me bring that up. 3 times 3 is 9. 10 minus 9 is 1. I don't have a zero remainder. Let me tack on, whoops, let me be blue there. Let me tack on another 0. I can bring that down. Now I have the question again. 3 goes into 10 how many times? 3 times 3 times 3 is 9. 10 minus 9 is 1. Tack on another 0. I kind of see that I'm just getting the same problem over and over, right? Over and over, I just ask how many times does 3 go into 10? It goes in 3 times, and I have a remainder of 1. Remainder of 1, tack on a 0, that makes a 10. 3 goes into 10 3 times. Remainder of 1, tack on a 0, I get a 10. 3 goes into 10 3 times, and so on. I see this is never going to stop, right? It's just going to keep going forever. In other words, I'm going to get another 3, and another 3, and another 3 from adding another 0, and another 0, and another 0. It's just going to keep going forever. So the decimal equivalent of 1/3 never terminates. Like 1.125 up here, like we got to the 5, we ended up with a 0 remainder, and that was it. If we tried to stick on another decimal place here, it would be just a whole bunch of zeros. There's nothing of substance after that 5. But here, 1/3 is like, sometimes we write it as 0.333 dot dot dot. It's just 0 point and then 3 is going on forever. There's a 3 in the 10th place, a 3 in the 100th place, a 3 in the 1000th place, a 3 in the 10,000th place, and so on down the line. This is kind of a, not a great notation, writing this dot 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 here. So we have a notation for this. I noticed that the 3 is what's repeating over and over. So I say 1/3 is 0.3 repeating. I put this bar, this horizontal bar above the 3, and that signifies the 3 keeps repeating. Now, a little note on notation, if in, say, just for instance, a different problem, if I had 0.271, 271, 271, 271, forever, if the 271 kept repeating, I would write this as 0.271 repeating like that. Or if I had something like, 1.235858558, and the 5/8 started repeating after a little while, I write this as 1.23. None of these repeat, then 5/8 repeating. So I'd make sure that that horizontal bar is only over the piece that's repeating. So I would not write something like that, because the 2 and the 3 aren't part of the repeating group. The 5/8 is the thing that keeps repeating after a while, and so I write a bar over it. And the last thing I want to point out is, just because something has a recognizable pattern does not necessarily mean it repeats. We can see the pattern here. We have a 1, then 1 0, and then a 1, then 2 zeros and a 1, and 3 zeros and a 1, and 4 zeros and a 1. But this isn't any kind of like, repeating thing like that. It's not like that. It turns out that a complete characterization of fractions, as ratios of one whole number to another, are decimals whose decimal expansion either terminates, like this one here, 1.125, and that's it, or repeats, something like this. So if a decimal terminates or repeats, I can write it as a fraction. If I have a ratio of 2 whole numbers, it will always either turn out to be a decimal expansion that terminates or that repeats. So the two are in a one-to-one correspondence that way. So the idea of a decimal that terminates or repeats is essentially equivalent to the idea of a fraction that's the ratio of whole numbers. Any questions on any of that so far? Okay, let's look at 2/9. Let's try to write 2/9 as a decimal. So again, I start by writing 2 divided by 9. Now I don't have anywhere to go here. 9 goes into 2 0 times. So I'll turn 2 into 2.0. Does 9 go into 20? Well, yes, it does. 9 goes into 20 2 times. 2 times 9 is 18. We have a remainder of 2, and we can kind of see where this is going. I bring down the 0, and I ask again, does 9 go into 20? Yes, it does. Goes in 2 times. 2 times 9 is 18. Remainder of 2. put a 0, bring it down, does 9 go into 20? We see that if we have two consecutive kind of remainders or like, intermediate remainders that are the same, I asked does 9 go into 20? Yes, it does. And then I ended up with a remainder of 2 that led to another 20. Clearly, this is going to repeat forever. If I end up with two consecutive remainders that are the same, I add a remainder of 2 here, remainder of 2 there, this will go on forever. So 2/9 is 0.2, and that 2 is what's repeating. As a little semantic note, it probably wouldn't be considered like completely incorrect if you wrote like something like that. I guess you can consider it as like the group of 3 2s repeating or something, but uh it's kind of bad form. We would want to write it just as the smallest group that repeats. That's the group that we want to indicate with the repeating bar. So we'd want to write it like this, 0.2 repeating, where the 2 is the thing that's repeating. Any questions so far? Okay, let's write 18/11 as a decimal. So 18 divided by 11. Does 11 go into 18? Yeah, it actually does. This is an improper fraction, so we have a whole part that's in here. 11 goes into 18 one time. 1 times 11 is 11, leaving me with a remainder of 7. So I could say that 18/11 is like 1 with a remainder of 7, or 1 and 7/11 or something like that as a mixed number. Or if I want to write it as a decimal, I turn my 18 into 18.0, bring the 0 down. I also encounter my decimal, so I bring my decimal up. 11 goes into 70. Well, I think that's 6 times. 6 times 11 is 66. So we get 4 left over. Not a remainder of 0 yet. Let me tack on a 0 at the end of the 18. Bring it down. 11 goes into 40. I think that's going to be 3 times. 3 times 11 is 33. Remainder of 7. At one point in the past, I had a remainder of 7. And now again, I have a remainder of 7. I think this is going to repeat. Let's go a couple more steps just to show that it does. 11 goes into 76 times. 6 times 11 is 66. Remainder of 4. 11 goes into 40 3 times. 3 times 11 is 33. Remainder of 7. And I see that I get my 7 again, right? If I see my remainder repeat like this, maybe I shouldn't say repeat at all, but I see, whoops, wrong one. See a remainder of 7, then 4, then 7, then 4, then 7, then 4. It's going to keep going like that. I know that this 6/3 is just going to keep repeating. So 18/11 is going to be 1.63, where the 6/3 is repeating. I know that this 6/3 is going to make another 6/3 and another, and so on down the line. Any questions on any of this? Okay, so let's look at simplifying 1/4 plus 10.75. And maybe we'll simplify this in 2 different ways. We'll simplify by converting everything to fractions and simplifying in fractions. Then we'll simplify by converting everything to decimals and simplifying in decimals. So if I convert everything to fractions, well, the 1/4 looks good already. 10.75, this is 10 and 75 hundredths, right? Well, I know that 1/4 is 25 hundredths. I can just multiply top and bottom by 25. I can use my commutative property of addition to switch these two. And I see I now have the sum of two fractions with a common denominator. I can add the numerators. Keep the same denominator. I get 100 over 100, or just 1 plus 10. That's just 11. I can also simplify by converting everything to decimals. 1/4, as we saw above, is just 0.25 plus 10.75. I want to do this decimal addition. I write down kind of the more expansive number first. I line up my decimal points because I'm in addition now. So when I'm adding, I make sure to line up my decimal points so that all the place values line up nicely. 5 plus 5 is 10, write the 0, carry the 1. 7 plus 2 is 9, plus 1 is 10, write the 0, carry the 1. Bring your decimal point down. 1 plus 0 plus 0 is 1. So we get 11.00, or just 11. So maybe in some problems, it's a little easier to convert everything to decimals and carry out the simplification there. In other problems, it might be easier to convert to fractions and carry out the simplification there. So for instance, 6.29 plus 21 out of 40, 21 over 40. Maybe here I'll convert everything to decimals. So I'll put this fraction, or take this fraction, rewrite it as a decimal, and then combine it together with 6.29. So 21 divided by 40. 40 does not go into 21. Or I could say 40 goes into 21 0 times. So I make that 21, 21.0, bring my decimal point up. 40 goes into 210 5 times. 5 times 40 is 200. And I get a remainder of 10. I stick another 0 on the end, bring it down. 40 goes into 100 twice. 2 times 40 is 80. Remainder of 20. Another 0, bring it down. 40 goes into 200 5 times. 5 times 40 is 200. Remainder of 0. Nothing substantive left to bring down. That is what 21 divided by 40 ends up being as a decimal, 0.525. And now I just have decimal addition to do. 6.29 plus 0.525. I'll put a little buffer 0 in there after the 9 and the 6.29. 0 plus 5 is 5. 9 plus 2 is 11. Write the 1, carry the 1. 5 plus 2 is 7, plus 1 is 8. Bring the decimal point down, and 6 plus 0 is 6. So it looks like the answer is 6.815. Or 6 and 815 thousandths. Could write it this way. Or I could write it as 6,815 over 1,000. And if I wrote it like this, I would probably want to go through and simplify that fraction a little bit. I probably also would want to simplify this one. There's at least a factor of 5 in there that we can divide out, but we'll leave that. We'll leave these the way that they are, because that's not really the focus of our work right now. Any questions on anything to this point? Okay, so we're going to take a little bit of a diversion here into a bit of geometry, finding the circumference and the area of a circle. Uh, so a circle, of course, is the set of points that are equidistant from another point called the center. So we have the center of a circle here, and the distance from the center to any of those points that makes up the circle is called the radius, and twice the radius is the diameter. The diameter is the line going from one side of the circle to the other side of the circle, passing through the center. It's the length of that line, the diameter. The circumference of the circle is the measurement going all the way around the circle. So if I pick whatever point on the circle I want to start at, I start walking around the circle and come back to where I started. If I had one of those little, you ever see those construction worker guys with the little wheelie things that they wheel along the ground and it just adds up the distance. So if I did that all the way around the circle, how far would I have walked? What would the measurement be? So that is the circumference. It's the perimeter of the circle. Now, I'm sure everybody has seen in the past this idea of pi. In geometry, pi is usually trademarked to be this number that's very important in circles. It's approximately 3.14. There are people who like to memorize lots of digits of pi. I don't know that many digits of pi, um, but some people think that it's a fun pastime. Note also that pi is approximately 22 over 7. That's another approximation for pi. It's a fraction that has a numerator and denominator that are fairly small numbers, and it also gives a result that's fairly close to the actual value of pi. As an exercise, write 22/7 as a decimal and show that it's approximately 3.14. Carry out that long division until you get 3.14, and you can show that that's approximately true. So our circumference, the formula for it, the perimeter of the circle, or one go around the circle, is 2 times pi times the radius, or we see that a diameter is just twice the radius. So 2 times radius is diameter. So the circumference is pi times the diameter. So really what pi is it's the ratio of the circumference to the diameter. That ratio is constant for any circle. If the circle is bigger or smaller, the ratio of the circumference to the diameter is pi. And the area of the circle is pi r squared. The area, this whole area on the inside here, is pi times the square of the radius. Note that our diameter and our radius and our circumference should all be measured in units of length. So for instance, let's say feet. Circumference should be, say, in feet. And we notice that diameter is in feet as well, as is, say, radius. So that all checks out. So pi is a unitless constant. It doesn't have any dimensions associated with it. Area should be, if we're measuring in feet, should be something like square feet. And we do see that coming in here. We have the radius being measured in feet, but it's getting squared. So we do get square feet out. So let's approximate the circumference and area of a circle with radius 3 feet. And let's try to answer as a decimal rounded to the 10th place. So the circumference has a radius of 3 feet. So that's 2 times pi times 3. And this is in feet. Or that's 6 pi. Or that's approximately 6 times 3.14 for the circumference. So if I do 3.14 times 6, 6 fours are 24. 6 ones are 6 plus 2 is 8. 6 threes are 18. 2 decimal places, 0 decimal places. My answer should have 2 decimal places. My circumference is about 18.84 feet. And my area is pi r squared, or pi times 9. 3 squared is 9, and that's in square feet. So what is 9 times pi? Well, that's approximately 9 times 3.14. 9 fours are 36. 9 ones are 9 plus 3 is 12. 9 threes are 27, 28. And again, I want 2 decimal places in my answer. My area is approximately 28.26 square feet. So we just need to know these two formulas and plug in and know the approximation for pi, and we're good to go. We can do all of the operations that we need to do now, provided we're given the formulas or know the formulas and the approximation for pi. And another view on this, on a similar problem: approximate the circumference and area of a circle with a radius of 3/4 of a meter. And here we want to answer as a fraction. So my circumference is 2 times pi times r, or 2 times pi times 3/4, or this is going to be, well, 2 times 3 divided by 4 pi, or 3/2 pi. So my circumference is exactly 3/2 pi, but pi isn't a fraction. But I can approximate it by the fraction 22/7. If I want to stay in fractions, I use the fraction approximation for pi. If I want to be in decimals, I use the decimal approximation for pi. So I want to stay in fractions here. I'll approximate pi as 22/7. I see I can divide out of 2. My circumference is approximately 3 times 11, or 33, divided by 7 as a fraction. And what's my area? And that's 33/7 meters. My area is pi r squared, or that's pi times 3/4 squared, or pi times 3/4 times 3/4. That is 9/16 pi. But again, pi is approximately 22/7 as a fraction. I have a factor of 2 that goes away, or that's going to be 99/56. So my area is approximately 99/56 square meters as a fraction. And that was perfect timing. We got to the end of what I wanted to get to, just 1 minute away from the end of class. Are there any questions on anything?